the previous lecture we have solved problems of free vibration of simple single degree freedom systems without damping using a Newtonian approach. Means that we consider the body which is executing oscillatory motion subjected to the various forces, both disturbing and the restoration, and then we form the equation of motion, and solution of the equation of motion yielded the subsequent result, which is a simple harmonic function of time. Sometimes it may be a bit inconvenient to draw the free body diagram or to conceive the problem as a one suitable for writing down the equation of motion in a straightforward manner. We will take some examples very soon. So there is another approach for solving the vibration problems of single degree freedom systems without damping. So in today's lecture we will discuss that approach, that is the energy approach, in solving simple free vibration problems. At the root of the whole philosophy or approach or method, you can say, is the fact that without any dissipation of energy, total mechanical energy in the system remains constant. So the total energy which is the sum of kinetic energy and potential energy, that remains constant. Now potential energy of course will consist of gravitational potential energy, plus elastic strain energy. So we know that for a simple single degree freedom system where the motion of the body is represented by one coordinate, the x. So kinetic energy of such a body will be written as half m x dot square, where x dot is the speed. Similarly, potential energy of a body will be half k x square plus where h is the height above the equilibrium position, g is the acceleration due to gravity, and the potential energy. Actually, in fact, in many cases this can be written as some function of x, that is height will be dependent on x. May not be exactly x, sometimes it will be exactly x, sometimes it will be dependent on x in a linear fashion. Now I think this is well known, because we know that if we take a spring of stiffness k and then subject this to a force at any instant, then we know the plot f versus x will be a straight line which is nothing but a. So, if we displace the mass up to x from equilibrium position, then the work done is nothing but the area under this curve, which is half a. This is known to us. So, the spring element will contain this much of strain energy, which is a potential energy, and if it changes its level, the mass, then this being the change in level, this will be the gravitational potential energy. So, therefore, the total energy of a system will be the kinetic energy plus potential energy. So, total energy is equal to kinetic energy plus potential energy, which is again nothing but now we will see that there are two possibilities. We can do one thing, that ddt of total energy is equal to 0. That is one approach. That means differentiating this, and remember that in most general situations this may be a function of it. So, differentiating this, we will get an equation in terms of x and its derivative, which is nothing but the equation of motion. So, we have derived the same equation of motion without taking help of free body diagram and the Newtonian approach. The simple possible case is, say, if we take up the simple spring mass system, where this is the equilibrium position and the displacement coordinate from the equilibrium position is x. So, at any position when it is deformed, say here, its total energy will be how much? Half m x dot square as the kinetic energy, and here since it is in the same level, there is no change in gravitational potential energy. So, we can consider the gravitational potential energy to be a constant or 0, whatever it is. Only the strain energy in the spring . So, applying this conservation principle, this yields mx 2 dot plus kx equal to 0. The same equation of motion which we derived by using Newton's second law. And then of course, it has to be solved. Similarly, we can take up another example where now if this happens to be the natural length of the spring, then obviously it will, under the action of gravity, stretch little bit, takes up the gravity, and let this be the equilibrium position, so that it has undergone a stretch of delta as we have seen before. So, and we measure the displacement coordinate from its equilibrium position where the spring is no longer in natural length. So, in this case, what will be the total energy? If this is K, this is M, total energy is kinetic energy, which is same as half m x dot square, and this amount of stretch in the spring will be half K into delta plus x, if delta is the stretch from its natural length to the position when it was in equilibrium under the action of gravity. So, the total stretch of the spring, since we are measuring x from its already stretched condition, which is the equilibrium position, then the total stretch in the spring will be this, and total amount of strain energy will be this. Minus, now it is falling in height. So, its potential energy, if we treat it to be 0 at this location, that is equilibrium position, then potential energy will decrease by, or it will be minus mg x when it has gone to a position x from its equilibrium position. So, this is the gravitational potential energy, this is the strain energy in the spring, this is the kinetic. So, now again taking the conservation principle and treating total energy to be constant, this ddt should be 0, and this will lead to what equation? Differentiate this with respect to time, it will be m x dot x2 dot plus k delta plus x minus m equal to 0. Here, of course, we have to write and then we are differentiating with respect to time. So, this term after differentiation becomes this term after differentiation with respect to time becomes this, and this term becomes this. So, obviously, all these x dot terms go out and we get, or m x2 dot plus k delta plus x minus mg equal to 0. Now, if we remember the condition that in equilibrium position when the amount of stretch was delta, then this was the condition when k delta was equal to mg. The spring force was balancing the gravity or gravitational. So, if you use this, you get finally mx2 dot plus k delta is equal to mg, so it gets cancelled. So, we get again the same differential equation. So, these are, I think you may think that these are trivial cases. What is the need of doing it in this roundabout way using the energy approach? So, we will now take up a case where it may not be so easy to frame the equation of motion and find out the natural frequency, because ultimately our objective is to find out the natural frequency of oscillation when the system is disturbed from its equilibrium position. Let us consider this example. A thin rod of length L and mass m is resting on a cylindrical surface. So this is the equilibrium position, and we also mentioned that the friction between this rod and the cylindrical surface is enough to prevent any sliding, so that it can only roll. Now, if we dip it little bit to bring it to this position, we have dipped it and left it. So we know that it will oscillate. Now we have to find out the natural frequency of oscillation of this. Here it may not be so easy for one to find out the natural frequency. Remember, here also it is a single degree freedom system, because without any rolling or without any slipping in pure rolling condition, the only thing what needs to be prescribed to explain or to prescribe its to describe its configuration is that angle theta from the horizontal position. So therefore, let us see if we can frame the equation of motion using the energy approach. Now the CG of the rod is here, and now it has gone here. So in the deformed condition or the displaced condition, the potential energy has increased. So if this is the point of contact, we know this angle is again theta, because this is 90 degrees, this is 90 degrees. So if this is theta, so this must be also theta. So therefore, let us find out first the kinetic energy. Now kinetic energy of a rigid body, we know, is the kinetic energy of the body treated as a particle and situated at the center of mass. That means half m into velocity of the center of mass square, plus take care of the rotation, it will be the moment half into moment of inertia of the rod or the body passing through it about an axis passing through the center of mass into theta dot. So what is the speed of this? Speed of this point is 0, because it is in contact with this body without any slipping, and this point's velocity is 0. So velocity of this point will be simply this length into theta dot. So half m, when we first treat the translational kinetic energy, half m into how much is this length? This length is nothing but r into theta. R into theta, that is this length approximately. Not approximately, exactly. And then theta dot is the angular velocity. So this point's velocity will be velocity of this point, which is 0, plus this square. This is the linear velocity of the center of mass, that is the length of this portion, into angular velocity, that is the linear velocity, plus half into moment of inertia of the rod about its center of mass is half ml, 1/12 half ml square. So half into moment of inertia about the center of mass into theta dot. So we can write this as half m r square theta dot square plus half 1/24 m L square theta. So that is the kinetic energy. Next we have to find out the potential energy. potential energy, there is no spring element, so therefore there will be no strain energy stored in the system. Only there will be gravitational potential energy, because the center of mass of the system is changing height. How much is the change in height? It is approximately this much. In reality, it will be r theta and this part. Now we have to keep in mind that theta is known. Without this, the problem becomes very complicated, nonlinear, and not practical. As a matter of fact, all non-small oscillations, large oscillations, are nonlinear and difficult to solve. So this we have to always keep in mind. So therefore, this arc length and cosine of theta, which is going to be approximately 1, is approximately the change in height. Now, how much is this? This much, we know this much is equal to r in, this length into theta. Minus, you have to subtract this much, that is the 8. So this approximately is equal to r theta is the length into theta is this total arc length minus this much is what? This is r cosine theta, r minus r cosine theta, minus r is 1 minus cosine theta. Now, which we already know, this is the total height change multiplied by n. We know already that this is equal to m into g r theta square minus 1 minus cosine theta. If you expand, it is 1 minus half theta square. So therefore, it will be 1 minus this, so it will be minus half r square. So this is approximately m g half r. This is an approximation considering theta to be small. So total energy is half m r square theta dot square plus 124. This is the total energy, and we apply now the conservation principle, which says that total energy is constant. That is, we differentiate with respect to time and put it equal to 0. This leads to what? Now differentiate this, it will be m r square theta into theta dot cube plus m r square theta dot theta 2 dot, that is the first term, plus 1 by 12 ml square theta dot theta 2 dot plus mg r theta dot. Now, we have to keep in mind that theta is small, theta dot also will be small. So, compared to these two terms, as you can see, this theta square the theta square term, the theta dot cube term, they can be considered to be very small and can be neglected. So what we are left with is 120 or 112 ml square theta 2 dot plus mg r theta is approximate. Removing this, so therefore we get the final form. This becomes our equation of motion or small oscillation. So we can see that energy approach can be very convenient in solving some problems which may not be that easily amenable to the Newtonian approach, which can definitely be done, but it will be more complicated. There is another approach to the energy method. We will see that. What we have used here is the principle of conservation of energy. Now, principle of conservation of energy, when used in this way, we get the differential equation. But there is another way we can look at the problem like this. When a system is oscillating, it is undergoing changes continuously. Now, when it is passing through equilibrium position, then if we consider that the equilibrium position system to have the minimum potential energy which we can equate to 0, and when it goes to end, then obviously it stops. That means its kinetic energy is 0. So, for small oscillations, always remember any oscillation can be written as any oscillation, whether it is angular, linear, if x is the parameter, displacement coordinate, then x as a function of time can be always written like this. We have seen that. So therefore, velocity or the speed so this will tell us maximum x that is x max is equal to capital X or the amplitude of oscillation. Similarly, maximum speed or x dot max is omega n. Now, what we have mentioned just a little while ago is that in this oscillating system where the total energy is constant, it is passing through equilibrium position when its potential energy is 0, and it is reaching the extreme ends when its kinetic energy is 0. So therefore, in the equilibrium position, the whole energy of the system is in kinetic form because potential energy is 0. Similarly, when it goes to the end, then its total energy is in potential form because kinetic energy is 0. And since the total energy remains constant, we can write that kinetic energy in the system, its maximum value has to be equal to potential energy of system mass, and both are equal to the total. So now what we can do, we can take this approach that we know for all small oscillations, oscillation is going to be simple harmonic. Only thing what is unknown and we have to find it out is the natural frequency omega n. So what we will do now, we will find out the expression of kinetic energy in the system and find out its maximum value and find out the expression for the potential energy of the system and find out its maximum value, and we will equate them. Since the kinetic energy term contains omega n, we will get an equation in omega n, and that way we can find out the value of omega n. So our simplest problem, for example, we will again take this one. So at this location, x dot is equal to omega n x, and when it goes to the extreme end, here x is equal to, when Pe is, Ke is 0, here Pe is 0. So what is the expression for kinetic energy? Half m x dot square. So Ke max is going to be half m, x dot's maximum value is omega n x. So will be and potential energy is here, gravitational potential energy remains same, we can put it equal to 0. Strain energy is the only potential energy, which is half a x square. Now if we equate kinetic energy max is equal to potential energy max, this will give us in this case half m omega n square capital X square is equal to potential energy maximum, which is half a x square cancelled, and this gives us directly the expression for. So this is another angle of the whole thing. We can use this concept that we find out the maximum kinetic energy and maximum potential energy, treating potential energy at the equilibrium position to be 0 and equating this. Thus we get an algebraic equation, not a differential equation, which we have to solve. Whereas on the other hand, we get the equation of motion, which is a differential equation, and we have to solve it. So this, of course, you may think is a very trivial problem. Let us take another problem. If we take a slightly involved problem, which may not be very convenient for Newtonian formulation, let us consider this problem of UT, which is filled with a liquid of density rho. The cross-sectional area of this tube is constant and is equal to A, and the length of this liquid column, total length, is L. Thus, we get the mass of the liquid column is nothing but rho into the volume of the liquid column, AL is the total mass. Now, when we displace, this is the equilibrium position. Now, let us consider that we have displaced it, and this end we have displaced by x. So, obviously, the other end will go up by the same amount. So, this is one extreme position where you leave, and then you leave it to oscillate. So, what happens? This water column will oscillate, as we know from our experience. So, we will apply now again the principle which we have just discussed, that find out the expression for the maximum kinetic energy and find out the expression for the minimum maximum potential energy. And all along we have to keep in mind that x is nothing but something like either sine or cosine. So, what is the maximum kinetic energy of this liquid column? Is when it is passing through the equilibrium position, the velocity is maximum, and we know velocity maximum of this case is this. This is the square of the speed at the equilibrium position when it is maximum, multiplied by half and the mass rho into L. This is the maximum kinetic energy of this. This has to be equated to the maximum potential energy, that means when it has reached one of the extreme ends. Suppose when this x is equal to capital X, that is the extreme end when it stops. How much is the increase in potential energy? Now, if we can treat that this amount of liquid has been taken here, so we get this configuration. And how much is the change in height? This is half x, this is again half x. So, in total change in height is half. So, what is the maximum change in height? That means this block has been placed here. So, when small x is capital X, that is maximum value, then that will be the maximum potential energy. So, how much is the increase in potential energy? First of all, the mass, that is rho into A into x. When x is equal to x, that is the volume and rho is the density. So, this is the mass of this block, which we are shifting by how much? We are shifting by an amount x into. So, this is the maximum potential energy. Equating the two, we get half rho A L x square omega n square equal to rho A x square So, here we get an algebraic equation in omega n, which tells us omega n square is equal to x square goes, A goes, rho goes, what remains? 2g. So, this is again so nicely done using this principle of energy, where we equate the maximum kinetic energy with maximum potential energy. Another example we will take up. So this problem is like this, that there is a cylindrical cavity and inside that a roller of radius small r and mass m is rolling, and you know that it will oscillate like this. We have imposed the condition that there is no slip between the inner surface of the cylindrical cavity with radius r and the outer surface of the cylinder. So therefore, it is a case of pure rolling. So if this be the case of pure rolling, so this point when it was touching here and it has rolled, then suppose it has gone there, that means when the cylinder was at this point, the point of contact P on the cylinder surface has gone now to this. So the condition for pure rolling tells us that this P and this point is Q, P prime Q, this R must be equal to PQ, this part. Their total length must be same because there is no slip between these two. So therefore, no slip condition tells us that R PQ will be equal to R P prime, or how much is this? This is capital R into theta. Theta is the center of the a line joined from the center of the fixed cylinder O to the center of the moving cylinder C. That theta tells us the position. Or we get PQ is equal to R into theta is equal to, and P prime Q is equal to, it is small r into the, if you consider this angle to be small phi, it will be, this is the condition which we get from those two. This is the kinematic constraint. Now, we consider theta to be a function of time, and that can be written as capital theta into sine omega when it executes the oscillation. Our objective is to find out omega n, and we will apply the same principle of equating potential energy and kinetic energy, their maximum. What is the maximum kinetic energy? Now, maximum kinetic energy will be when it is passing through the equilibrium position, and it will have a translational energy which is given by the mass of this rolling cylinder into half of the speed square. So it will be half into m, and what is the speed of its center? It will be r minus r into theta dot. This is the speed and the square. This is the transitional part of the kinetic energy of the cylinder. Rotational part will be half, and its moment of inertia is half mr square into theta dot is the angular velocity. Sorry, theta dot. We have to find out the angular velocity of the rolling of this. So therefore, we have to find out Now I will explain this little bit. What is the angular speed of this? Now when it has gone from here to here, what is the amount of rotation? You will find the amount of rotation is given that originally this radius, for example, P prime, was vertical here, P was here, and this was the position of this radius. Now it is here. So therefore, the rotation is given by this angle, which is phi, that is the total angle, minus this, which is nothing but theta. So amount of rotation of this smaller cylinder is not phi, but phi minus theta. So its angular velocity of this rolling cylinder will be phi minus theta's time derivative, that is phi dot minus theta dot. That is the kinetic energy maximum value. Not maximum value, sorry, this is still not maximum, it is kinetic energy. Potential energy, similarly, we can write, the potential energy will be only gravitational potential, as you can see. And that is m into g how much height it has increased? It was here, now it has gone there. It is this, which is r minus small r minus r minus small r cosine. So it will be and when theta is small, because small oscillation, then this can be expanded and it can be written as r. One minus cosine theta approximately half theta square, neglecting the higher order. Now we have one quantity phi we have to remove. Now from this equation we find phi is nothing but, so phi dot minus theta dot is nothing but r by r minus 1 into. Thus, and we also know, since theta is like this, so it will give us theta maximum so Ke maximum will be equal to half m r minus r square. Now theta dot square maximum will be omega n square. This term will give us 1/4 m r square, and theta phi dot minus theta dot is this. So this is the maximum K, and which on simplification will be 3/4 m Similarly, E max will be equal to half m g and equating what we get, 3/4 m and omega n square is approximately that's the answer we get. So here is find that the problem, if we try to solve using Newtonian approach, will be very difficult. We have taken the energy approach, where of course conservation principle has been used. We could also add the two and differentiate with respect to time and get a differential equation in theta, solving which we could get the same natural frequency. On the other hand, we have assumed that all small oscillations are simple harmonic functions of time, and by then equating the maximum kinetic energy with maximum potential energy, we get an algebraic equation for the natural frequency, which gives the result like this. So I think one should practice both approaches. Sometimes Newtonian approach may be more convenient, but in many cases you will find that the energy approach also gives the result. You have to also keep in mind that these are all approximate solutions considering the small oscillation approximation. That's why we are always keeping this approximate